Hello, it's Omid Rebi who presents the paper of Lifelong Self-Adaptation. Self-Adaptation meets lifelong machine learning. Let's start with the problem context. This is a general architecture of a self-adaptive system based on the MAPE-K feedback loop, which is supported by machine learning module. Here, the managing system works for satisfying some quality goals in the managed system by monitoring and accordingly adapting it. Hence, the managing system solves the adaptation problem by decision making for the best adaptation option selection. An example of adaptation problem can be improving the resource allocation in cloud. And learning problem is a subset of the adaptation problem that dealing with it is delegated to the machine learning component. An example of learning problem is predicting resource usage that can be a subset of the improving resource allocation problem in cloud. This plot represents the increasing trend of machine learning usage in self-adaptive systems as a support to deal with uncertainties. Examples of these supports are keep runtime models up to date, predict or analyze resource usage, detect or predict anomalies. Although machine learning methods support self-adaptive system and decision making, they can be cause of uncertainties in the system and they cannot deal with new emerging tasks like concept drift automatically. In other words, these methods are working based on some predefined learning tasks. So the research question of this paper is how to enable self-adaptive systems that use machine learning techniques to deal with new and changing learning tasks during operation. Let's see an example to understand better the research question here. This is a topology of an IoT system with some numbers of battery-powered modes that measure parameters in the environment and send the data via a wireless multi-hub network to a central gateway where users can use the data. These sensors can send and receive messages over a wireless link. The quality properties of interest here are packet loss and energy consumption. These graphs show the utility preferences of the stakeholders for the qualities of interest. The utility of a network configuration is defined as the weighted sum of preferences associated with the quality properties. The quality properties are affected by uncertainties. Suppose that there are two types of uncertainties here. First, network interference caused by environmental conditions, such as weather fluctuations, and second, a load of messages generated by modes that fluctuate based on different factors, such as the presence of people in the environment. Note that the network interference affects the signal to noise ratio that determines packet loss. To maximize the utility, we have a managing system at the gateway that monitors the managed system and its environment and adapts the network settings in each cycle. The power setting of each node and distribution of the messages along the network links can be set by the managing system. To select a configuration, the managing system uses the stochastic gradient descent that predicts the quality attributes of the adaptation options. Also, an additional setting allows switching between a stochastic gradient descent method and another method called Hafting adaptive tree for prediction. The problem is now that the distributions of input data that is used by the regressor may drift over time. This figure shows how the global network interference changes when sudden concept drift occurs. Such a concept drift may, for instance, occur due to construction works in the neighborhood of the IoT network, where some machinery may periodically produce extra noise, affecting the signal to noise ratio of the network links. Now we can see the distribution of the signed difference between the packet loss predicted by a stochastic gradient descent regressor and the true best options that are based on the true values of the quality properties, we use here a scenario of 1500 adaptation cycles without and with drift. Obviously, the figure points to a significant increase in packet loss. So the underlying problem is that concept drift introduces new emerging learning tasks that the regressors cannot handle it. Now we briefly describe the basic principles of lifelong machine learning that provides the basis for lifelong self-adaptation. That is our novel proposed approach to tackle the explained research problem. Technically, lifelong machine learning is a continuous learning process of a learner. Assume that at some point in time, the learner has performed a sequence of learning tasks and call them as previous tasks. When the learner identifies a new task, it can leverage past knowledge maintained in a knowledge base to help learn the new task. After completing learning new task, the knowledge base is updated with new gained knowledge, for example, using intermediate and final results obtained via learning. At this point, updating the knowledge can involve checking consistency, reasoning, and mining meta-knowledge. We now introduce the novel approach of lifelong self-adaptation that enables self-adaptive systems that use machine learning techniques to deal with new learning tasks during operation. So here we can see the general architecture of a self-adaptive system works based on the MAPE-K feedback loop and supported by the machine learning. Lifelong learning loop as a meta layer on top of the managing system, leveraging the principles of lifelong machine learning. Here, the knowledge manager stores all knowledge that is relevant to the learning tasks of the managing system's learner. In each adaptation cycle, the knowledge manager collects a knowledge triple, including first, the properties and uncertainties of the system and its environment. Second, the data of the managing system relevant to the learning tasks, for example, settings of the learner, and the actions applied by the managing system to the managed system. Depending on the domain, the knowledge manager may reason about new knowledge, mine the knowledge, or extracting meta-knowledge, such as ontology. The meta-knowledge can be used by the other components of the lifelong learning loop to enhance their performance. Also, the knowledge manager may synthesize parts of the knowledge to manage the amount of stored knowledge. For example, outdated or redundant tuples may be marked or removed. Task manager is responsible for detecting new learning tasks. It periodically retrieves new knowledge triples from the knowledge manager, then identifies task labels for the retrieved knowledge triples. A knowledge triple can be assigned the label of an existing task or a new task. Each new task label represents a significant change in the data of the knowledge triples. For example, a significant change in the distribution of the data observed from the environment and managed system. Afterwards, the task manager returns the knowledge triples with the assigned task labels to the knowledge manager that updates the knowledge accordingly. Finally, the task manager informs the knowledge-based learner about the new task, new detected task. Now, knowledge-based learner decides how to evolve the learning models of the learner, of the managing systems learner, based on the collected knowledge and associated tasks, and then enacts the evolution of the learning models. To collect the knowledge that it needs for the detected learning tasks, the knowledge-based learner queries the task-based knowledge miner. And now the task-based knowledge miner retrieves the knowledge triples associated with a given task from the knowledge tasks repository. The task-based knowledge miner can mine the knowledge repositories of the knowledge manager, for example, retrieving knowledge of learning tasks that are related to the task requested by the knowledge-based learner from the previous steps. The task-based knowledge miner may collect knowledge from stakeholders, for instance, to confirm labels of knowledge triples, like what happened in active learning. And the miner uses new knowledge to update the knowledge maintained in the repositories by the knowledge manager. For example, it may update meta knowledge about related tasks or add data to the knowledge provided by stakeholders. Finally, the task-based knowledge miner returns task-specific data to knowledge-based learner. The knowledge-based learner then uses the collected data to evolve the learning models of the managing system. This evolution is domain-specific and depends on the type of learner at hand. For example, tuning or retraining the learning models for existing tasks, or generating and training new learning models for newly detected tasks. In the end, the knowledge-based learner updates the learning models of the managing system. Now let's employ this proposed framework to tackle the illustrated example. Here, Knowledge Manager collects 20 new knowledge triples per cycle of lifelong learning loop. Input and the triples are packet loss and energy consumption of the system, and signal to noise ratio for all links, and the load of messages for each mode. State is metadata about a learner, including the configuration of the learner, such as the scalar used, the input vectors that include the adaptation options, and the corresponding target values predicted by the learning model. And finally, the output are the adaptation actions applied for the selected adaptation option. Task Manager detects new tasks. And the new task here is new distribution of features in the input data of knowledge triples. In more detail, suppose at some point in time, the system has knowledge about a set of previously detected tasks. These tasks have corresponding data sets, each data set consisting of knowledge triples, and their corresponding autoencoders. When triggered, the task manager determines the statistical similarity between the outputs of each autoencoder and the inputs of the newly observed knowledge triples, and the outputs of the autoencoder and its corresponding dataset. If the similarity is below a given threshold for all autoencoders, the task manager introduces a new task with new knowledge triples. Then the task manager instantiates a new autoencoder for which we use a Bayesian optimizer. If the similarity is greater than a threshold for at least one autoencoder, for example, autoencoder J, the task manager assigns label TJ to the corresponding triples based on the highest achieved similarity by the Jth autoencoder. As we explained, knowledge-based learner evolves the learning models. When informed about a detected task, the knowledge-based learner queries appropriate knowledge specific to the task from the task-based knowledge miner. Based on the collected data, the knowledge-based learner determines the best learning models by optimizing the hyperparameters of each learning model using a Bayesian optimizer. Then it trains the best model based on the collected training data. When all learning models are trained, they are updated in the knowledge repository of the feedback loop. Finally, the task-based knowledge miner fetches the sets of knowledge triples from the knowledge manager for the tasks queried by the knowledge-based learner. We limit the fetched data to keep the training time of the knowledge-based learner at a constant and appropriate level. The current instance of the task-based knowledge miner apply no special mining. Now it's time to see some evaluation results about the performance of the lifelong self-adaptation to alleviate the loss-related issue. This figure summarizes the results for packet loss of the network with different approaches. From left to right, first the baseline, which is the result of maximizing the expected utility based on the quality attributes true values in each adaptation cycle. Second, state-of-the-art approach that uses stochastic gradient descent regressors that retrains learning models in each adaptation cycle with all previously collected data. Third, incremental learning with a stochastic gradient descent regressor, but without a lifelong learning loop. This one presented in the illustrated issue. Fourth, lifelong self-adaptation with a lifelong learning loop and a stochastic gradient regressor. And finally, lifelong self-adaptation with a lifelong learning loop that can switch between the learner of the managing system, which are a stochastic gradient descent regressor and a Hafting adaptive tree regressor. This last approach allows comparing the effect of incorporating Hafting adaptive tree, which is a learning method that is known to be suitable for dealing with concept drift of input data. We can observe two key points. First, all solutions to resolve the concept drift are approximately working close to the baseline. Also, we can observe that almost 10% gap between the median of the packet loss in scenario of learning a stochastic gradient descent without lifelong learning loop in comparison with other proposed methods. Also, in terms of the expected utility, we can see the gap with size 0.1 out of 1. Therefore, all methods have improved the quality of the system under concept drift as well. However, the advantage of methods that are employing the lifelong learning loop over retraining the learning models with the entire data story is the performance. As we see in this graph, the training data of the learners are nearly constant over time under taking the lifelong self-adaptation techniques. In opposite, the training time will increase polynomially over time for the retraining method. Finally, we'll look at how many new tasks the lifelong learning loop detected in this evaluation scenario. This figure shows that in total, 18 different new tasks were detected over the period of 1500 cycles. Obviously, the number of detected tasks is increasing over time. In some self-adaptive systems, are characterized by their ability to deal with uncertainty. Machine learning techniques, on the other hand, which are increasingly used in self-adaptive systems, face challenges with uncertainties that were not considered as learning tasks during design. To deal with new learning tasks, we presented lifelong self-adaptation, a novel approach to self-adaptation that enhances self-adaptive systems that use machine learning techniques with a lifelong learning layer. We presented an architecture for lifelong self-adaptation and applied it to deal with two types of concept drift in two domains. The evaluation results show that lifelong self-adaptation effectively resolves the problem of concept drift. As future works, we plan to study and apply lifelong self-adaptation for other types of concept drift, in particular class drift and novel class appearance. Then we plan to investigate how lifelong self-adaptation can be used to deal with new and changing adaptation goals in an ML supported system, which is particularly challenging example of uncertainties for self-adaptive systems. Thank you for your attention.